Can you hear me? Good. So yeah, let's continue from where we left yesterday. You all understand this figure by now. Complexity. This is signal to noise. This is very often the challenge in astronomy because we have very noisy data. But another challenge is to write this axis, I should say this one, the complexity axis, and try to extract information and trends from complex data sets. All right. As we discussed, when we are writing this axis, one of the challenges is whether or not we have the right language to describe things. If you remember this, as you know, if we do not have the right vocabulary, it can be very difficult to just describe what we see. And that's the same when it comes to data analysis. If we don't have the right tools, extracting information can be quite challenging. We thought about the complexity of such an image, and in this case, complexity can be thought of as description length. The question is, how many numbers do I need to describe this image? All right, so an image like this typically will have, several million pixels. Now, if I tell you that we have about 1,000 sources in this image, my question for you to start is, how many numbers do I need to have a good approximation for this image? Okay, so I'm going to say it again. Let's say we have 1,000 sources in this image. From what we discussed yesterday, can you try to come up with an estimate of how many numbers we need to describe this? And you can discuss that with your neighbor to see if you come up with the same estimates. Okay, it's still working. All right. It is time to come up with an estimate. What did you get? How many numbers do you need to describe this image? Yes, go ahead.
Just over 10, so
over 10 numbers to describe the entire image?
Per source. Per source.
Ah, okay, per source. Okay, so why would you come up with about 10 numbers per source? What are those numbers?
So they're all of the image moments, like barycenters and moments.
There's an infinite number of moments.
Yeah, I think
Yeah.
so. Like the first two, at least.
The first two, what is the first one for you?
So barycenter.
The barycenter.
Mean
So,
position in X, mean position
okay,
in Y.
before going to first order, what about looking at the zeroth order moment, which is the total brightness or intensity?
Well, that's
Okay, so that's one number. So that's total. That's intensity. There's one number. Yes, that's a good point. Let's start with one band first. Okay, so in one band we have intensity, then we have x and y, the mean positions, and then we have sigma x, sigma y, and we have also the cross sigma xy. Okay, I'm going to square that. Yeah, that's fine. We have three numbers to describe the size and the orientation. Okay, it's the axis ratio and the orientation. We need three numbers for that in 2D. And so these numbers will allow me to describe this ellipse. Okay, and that ellipse, as we saw, is going to be a reasonable approximation for the sources that I have. Okay, so that's 6 numbers. That's one band. How many bands are we having here? Roughly. At least 3. So this is the decal survey, and I do not remember exactly, but usually it's it's more 5 in astronomy for optical surveys like this one. Okay, sorry. Decals is 3 only. Thank you. All right, so then let's use 3. So we have 6, okay, 6 numbers times 3 bands. And I'm going to write here 6 moments, 6 for the moments, times 3 bands times 10 to the 3 sources. That's about 20,000 numbers. Okay, so that's the right order of magnitude. Of course, we could expand this a little bit to be more accurate, but that's about what we need. And this has to be compared with the number of pixels we have in the raw image. Okay, and this is just one image. It's a composite, but in reality, you need one image per band, so you would need 3 images like this one. So it would be times 3 for the number of pixels. Okay, so what you can see here is that by having used this representation, we have done a huge dimensionality reduction. Okay, and if I show it visually, this is the number of pixels in the original image, and this is a lower estimate. It's only 1 million pixels. Okay, and then we can shrink things down to about 10. We got 20, but that's about the same. Okay, 10,000, 20,000. So this is the type of dimensionality reduction we can do because we have the right language. Okay, if you remember the pictures we saw yesterday of nebulae and so on, we cannot use this moment approach to describe what we see. All right, good. So in such a case, things are easy. We know how to do it, and what we are going to see later today and tomorrow is how to deal with more complex images. An important concept that I introduced yesterday is the principle of maximum entropy. This is extremely powerful, and that's what should guide you in the way you think about distributions in many ways. One way that I would like to state very clearly is when you do Bayesian inference. So David talked a lot about this. We have the posterior, the likelihood, the prior, and the evidence. What I would like to say here is that there is always this mysterious prior when you do Bayesian inference. Okay, and people might have different priors. The prior, and that's what James taught us, the prior has to be, if you want to do things well, it has to be a maximum entropy distribution. It has to describe what you know, and it has to describe your ignorance about everything else. Okay, and if you remember, the maximum entropy principle is using what we know, the constraints, and then saying that our ignorance about everything else is maximum, and we can use this Lagrange multiplier technique to write this down. Okay, so remember, your prior distribution here should be motivated by the maximum entropy principle. Okay, so it's not as mysterious as it might sound. Then, what we can do is to use this maximum entropy principle to derive many of the distributions that are important in statistics. Okay, so when I studied statistics as a student, I always struggled with these kind of things. Okay, so those are the outlines of some books. And usually they dump very early on a list of distributions. Those are the 15 distributions that are important. You know, those are the 12 distributions you should know. Those are the 20 distributions you should know, etc., etc. And very often they are not motivated or organized. Okay, so this is even a book that, an entire book that lists as many distributions as you can imagine. And it's very easy to get lost, especially to get lost with the mathematics and the equations without understanding exactly what's going on there. And this is often the case when we do not have a map to navigate in the space and understand where we are and where to go. Some people have come up with maps of statistical distributions. This is one example. This is telling you that if you do some changes of variables, you can move from one to another, etc. Personally, I don't feel better having such a map than a very long list of distributions. So what we can do is to try to come up with such a map using the principle of maximum entropy. I showed you yesterday, this is from Wikipedia. You can re-express many of the important distributions you find in physics using moments and the maximum entropy principle. So let's try to organize this a little bit. And what I'm going to do here is just to start with the simplest distribution we can generate using the maximum entropy principle. Okay, so I'm going to start with this. I just invoke the maximum entropy principle. Okay, and by doing this, I maximize the entropy. Okay, so I maximize the entropy of my distribution given some constraints. Okay. So what are the constraints? Okay, so let's start with no constraints at all. If I don't have any constraints, I just know that I have a random variable that's going to be, you know, between A and B, or x min, x max. What is the maximum entropy distribution? If you remember, the solution of this is the exponential of the constraint. Okay, and so here, there's no constraint. So what do I get? I get the uniform distribution, the flat distribution. Okay, you can think of it as e to the power 0. Okay, so here I'm going to get the uniform distribution. Okay, so it's just flat. Now let's add one constraint. I'm going to have a constraint on the mean. Okay, so the mean of x now is set to some value. What is the maximum entropy distribution? I know the answer is there, but I would like you to tell me. It's very simple. You just take the exponential of that. Okay, so if you remember the constraint is it's a moment of some function f of x, which is set to something. So what is the constraint here? Okay, so the constraint is just we have set this quantity to some number. Therefore, the distribution that I get is the exponential distribution. All right. I have another constraint. It's going to be now a constraint on the variance. What do I get? Okay, I get the Gaussian distribution. Now I have a constraint on the geometric mean. What do I get? It's harder to find in this list because it has a different name. You get the power law distribution. Right. So you get x to the 1 minus alpha here. Okay. And now, what you can do, you can combine different constraints. Okay, you can have different constraints at the same time, or you can start to play with these distributions. You can add random variables that are drawn from these distributions, and you can build more complex distributions. Okay, so for example, we have a Gaussian distribution here. Okay, so what happens if I take the sum of Gaussian distributions? What kind of distribution do I get? Another Gaussian distribution, right? So if I take the sum, okay, so if I take the sum of x, and x is going to be drawn from this distribution, I go back to the Gaussian distribution. What happens if I take the sum of x squared, and x is drawn from a Gaussian distribution? You know that distribution, the sum of x squared. Yeah. Okay, so if you take now the sum of x squared, okay, you get the chi-square distribution. Okay, the chi-square distribution is a sum of the square of random variables that are drawn from a Gaussian distribution. Okay, that's the distribution that's going to describe the residuals typically that you have when you do your fitting. Okay. All right, so this is just for you to understand that there is actually quite some interesting and simple structure behind these distributions, and you can generate all of them using maximum entropy. I'm going to give you another one. This is the distribution that's going to describe, for example, arrival times. Okay, so if you have a constraint on a rate, okay, so let's say that x is a positive random variable like time, okay, arrival time. How long do you have to wait for the next bus to arrive? How long do you have to wait for the next particle to be emitted? It's going to follow an exponential distribution. Okay, so this is the probability that will describe the next event. Now, if you want to ask, how long do you need to wait for n events to arrive? Okay, so it's basically a sum of n random variables that are drawn from these distributions. Do you know what you get? You get a gamma distribution, if you have seen it before. It's also called the Erlang distribution. And now if you reverse the question and you say, if I wait for a certain delta x or delta t, how many events will I have in that interval? Okay, so how many n in some delta x or delta t? Okay, so here we are counting. What is this distribution? That's the Poisson distribution. All right. Okay, and that's already like a fair collection of distributions that you encounter in physics and in your data analysis. All right, and I hope that this is going to help you understand where they come from. Okay. And it's all very simple. You want to maximize your ignorance about everything else and just use a few constraints that you know. Okay, so you can build these distributions. You know what kind of information is needed in order to generate them. Okay, I'm happy to discuss this more with you later in the day or tomorrow if you have questions about this. Yes?
Does the operation of random variable translate into constraint of maximum entropy?
Can you say that again?
So does the operation on random variable translate into something in the maximum entropy?
Not directly, but there are, for example, you can get to some of these distributions, you can get directly, to some of these distributions here by also, having a mix of constraints on a mix of, of constraints. So for example, the chi-square distribution, okay, you can also obtain it directly from maximum entropy by having a constraint on the mean and a constraint on the geometric mean together.
But is there any physical intuition how you could do the additional constraint
the mapping between this and the trajectories there is not obvious to me. No. What this shows, I mean, this is basically trying to mix constraints on the mean, the geometric mean, the variance, and a couple of other things. But if you just take those three quantities, you can see that many of these distributions, they map onto, so each distribution is going to be one point in this space of constraints, where the constraints are arithmetic mean, geometric mean, and variance, for example. Okay, so you have a space of distributions, and all of those will be just, individual coordinates in that space. The mapping between this and these trajectories is not at all obvious to me. Maybe there is one, I don't know. Okay. So let's continue thinking about data. All right, so now let's talk about images. This is an image from the MNIST dataset. And the one on the right is the same, but we've shuffled the pixels. Okay, so all the information is preserved. As long as you remember the mapping going from the left to the right, all the information is there. Now, when you have an image, you have two ways to think about it. You can have a distribution of pixels in 2D, or a distribution of flux in 2D. Or you can think of a space of, so if n-pix is the number of pixels along one dimension, we have n-pix square, and you can think of that image, or any image, to be just one single point in a space which will have n-pix square dimensions. Okay, so I'm going to say that again. So one image, okay, will correspond to 1 point in a space of n-pix square dimensions. Okay, so for a standard image of 1,000 by 1,000 pixels, an image would be just one coordinate in a space of 1 million dimensions. Along each axis, okay, each axis would correspond to 1 pixel of the image, and the value of the coordinates along each axis is just going to be the intensity of that pixel. Okay, so there are these two ways of thinking about images. Now, if we think about an image as the second possibility, and we have lots of images, we can try, so each image is going to be 1 point in this high-dimensional space. We have lots of images, so we are going to have a cloud of points. Okay. And what we can do is to look at the properties of these clouds of points. All right, so I have some high-dimensional space. My blackboard here only has, my whiteboard has only 2, so I'm going to restrict myself to 2, but imagine 1 million. One image would be one coordinate. And now if I have many images of the same type, they are likely to form a cloud like this. Okay. If that's the case, we see that there is some simplicity here, and we can make use of that. And there are a number of techniques that do so. One that you all know is principal component analysis. So what we can do, okay, this is a visualization of PCA. Let's imagine that we have lots of pictures of faces, and the key point here is that they are aligned. Each of these faces corresponds to 1 point in a space that has, I think it's, 64 square dimensions here. And what we can do with principal component analysis is to try to find the principal directions here. So one will be like this, and another one will be like this. Okay, I will have 64 square dimensions, or 64 squares vectors for my principal axis. And if I order them by their magnitude, okay, I can keep the first n vectors because they will be more important. They have larger magnitudes. And that's going to give me a basis set, or eigenvectors. I can use these eigenvectors to reconstruct any of my images. Okay, and so what is shown here, okay, so we have thousands of these images. Each of them is 1 point in this space. We do a PCA analysis, so we basically we diagonalize the covariance of these images, okay, to find the principal axis. Then we get eigenvectors, and this is showing the beginning of the list of eigenvectors. So first we have the mean. This is the mean phase over the entire data set. Then we have eigenvector number 1, okay, which is going to carry most of the variance. And as you can see, the one at the top next to the mean. So what I should say is that when it's black, it's positive, and then when it's red, it's negative, okay? Negative and positive values. And so what you see is that this is a tilt of the face, okay? Because they are not all exactly aligned with the camera. We have another tilt which is up and down, etc., etc. Okay, so here I get an orthonormal basis of vectors. And what I can do, I can re-express any image using that basis set. Okay, so this gives me a language to express images of faces. So what I can do, I can pick a face. Okay, this is one image. I can project it onto that basis set. I get some coefficients. Those are the coefficients for that image. And I can reconstruct the image just using the coefficients here and the basis set. Okay, that's what you get. And what is very interesting with PCA is that the eigenvectors are ordered by magnitude. So I can truncate. So these eigenvectors probably don't do very much. So I can truncate this. I can decide to keep 10 vectors, 20 vectors, 5 vectors. It's up to me. It's up to you, depending on how much of the variance you want to capture. So you can do that to reduce the dimensionality of your data set and re-express your objects using a new language. So this is your new language here. All right? Is that a good language? Depends on what you want to do. The problem here is that interpretability is not always obvious. What is this? What is this? I don't know. There are other techniques that are useful. One that was introduced 20 years ago is called non-negative matrix factorization. The idea is the same here, but instead of requiring our basis set to be a set of orthogonal vectors, we have a different requirement here. We want the basis set to have only positive values. Okay, so the main difference between PCA and here, so all the red that we find for PCA, remember it's positive and negative, the red is completely gone here. Okay, and we are left only with positive quantities. So the basis set is completely different. But it's all positive, and that can be a very good property, especially as physicists, if you want to decompose quantities that correspond to energy, photon counts, and other quantities where you do not expect any negative value. This is going to be an interesting language to use. And so same story, you can take one of your objects, you can project it onto that basis set, you get some coefficients, and you can reconstruct the object just from the coefficients. Okay, and again, the key point here is that you need much fewer coefficients, or you can, and you should use much fewer coefficients than the actual number of pixels in the original image. What can you say about the differences between this basis set? So the obvious one is that this has positive and negative values compared to NMF. What is the other key difference between the two? Yes? The NMF does not have a mean. That's a very, it does not use the mean as a reference point exactly. So what happens with PCA is that all of these vectors are encoding deviations from the mean. Okay, so the mean of the data set is very important here. It has a key role. Okay, sometimes you have data sets for which the mean is not representative at all. Imagine you have two populations, population A and population B, okay? The mean between the two is going to be a point halfway between the two populations, but you might have no data here. There might be no physical object. If you use PCA, you always have to refer to the mean of the data set. So any representation that you are going to have will always refer to the mean. Okay, and that can be a disadvantage in many cases. What else? Yes. By decreasing power, what do you mean? So that's right. So the magnitude of these vectors So the corresponding eigenvalues are decreasing. And so that order is meaningful for PCA. It is not that meaningful for NMF. Yes? Yes? Yes, okay, so if you have some noise and the noise will sometimes give rise to negative values, then yes, NMF it will give you different results, okay, because NMF will not be able to account for these lower fluctuations the same way, yes. So if what you want is to extract something that's positive, yes, this will do what you want. Yes? Okay, so why can you see it here and why you cannot see it there? What's the difference? There's one important property that no one has mentioned clearly yet. I agree with you that those features here are very hard to recognize. But what allows you to recognize things here? Okay, we are getting there, but what allows the contrast here? There is something very striking about these vectors. It is sparse, exactly. Okay, it's mostly white, okay, which is not the case for PCA. For PCA, you have almost no zero values, okay? But here, okay, white is exactly 0, okay? And most of the vectors, have pixels set to 0. So this is a sparse representation. So it's only a small fraction of the pixels for each vector here that is non-zero, okay? And that can be a very useful property. And that's also why you can recognize parts of the objects, eyes and nose and so on. So that's what makes them recognizable. Okay, and so what this technique does is that so it's sparse, and in addition there is some continuity here. Okay, so it's trying to extract contiguous parts of the objects. Okay, you don't find it could be sparse in the sense that just a small fraction of the pixels are set to black, but those pixels could be all over the place. Okay, but the pixels are grouped together, and that's also a very interesting property. Okay, so it's taking into account this continuity of the variations. Okay, so I'm going to show you one astronomical application of this. We are going to use 1D objects, quasi-spectra. So quasi-spectra come with a lot of variability. They have different slopes, different emission line shapes, different line ratios, and so on and so on. So describing them is, there's some complexity into them. And so what one can do, one can take thousands of quasi-spectra. They are all aligned in res frame. And one can apply this non-negative matrix factorization technique to get a basis set. And this is what you get. Okay, so that's the equivalent of the images that we saw before. Those are 5 vectors from the basis set. As you can see, they are all positive, which is good because they describe flux as a function of wavelengths, and we expect this to be positive. And what is very nice is that without knowing anything about physics, it decomposes the signal, the quasi-spectra, as a function of different vectors that are physically meaningful. Okay, so what we get here, we get forbidden lines, we get hydrogen lines, we get that are narrow, we get broad lines at the top, etc., etc. Okay. Once we have a basis set like this, what we can do, we can take any spectrum, we can project it onto that basis set, and we can re-express it just using a few numbers. And those are some examples. Okay, so in black, that's the data, and in red, or in blue, but that's almost the same, you get a reconstructed spectrum, and this spectra are reconstructed just using 10 numbers. Okay? So we have about 2,000 pixels in this direction, but we can re-express robustly the spectra using just 10 numbers from a basis set of 10 dimensions. Okay? We could have done the same with PCA, but the eigenvectors or the eigenspectra would be different because they could be positive or negative, and they would always make a reference to the mean. All right. So we've discussed this a little bit, but let's try to go a bit deeper into it now. So let's just focus on PCA for a moment, and I'm going to ask you to discuss with your neighbor and come up with pros and cons for PCA. So for especially, what are the limitations of PCAs? What are the cons of using such a dimensionality reduction technique? And later we will see how we can go beyond that. So you have a couple of minutes to discuss the pros and cons of PCA, and you can tell me what you find. All right. Let's summarize your findings. Okay, who wants to start? What is nice about PCA? Let's have good things to say about PCA. They are all easy. It's fast. That's good, but yes, okay. Others are fast too. So what is the fundamental property of the eigenvectors that we get? They are orthogonal, okay? And that can be a very, very useful property, okay? You know that you can take the dot product between any of them, you'll get 0, okay? So, okay. Eigenvectors are orthogonal, and that's a very important property, okay? PCA is the only one that will give you this property, okay? That's basically almost the definition. Okay. Another one? Yes?
It sort of tells you the number of numbers that you might need in order to label a non-memory set.
That's right. So basically what I'm going to say here is that the eigenvectors are orthogonal and they describe the variance. If that's close enough to what you are saying.
I think the part more is that they're interpreted.
They may be interpreted.
You mean physically no.
Okay, so they describe the fraction of variance. Okay, so each eigenvector, okay, is going to encode for a fraction of the variance. And because they are ordered for PCA, you know that the first eigenvector will describe most of the variance. So that's a good point to start. The next one will have less variance attached to it, etc., etc. Yes?
Well, there's a criterion for saying when they're no longer significant.
That's right. Okay. So one can, so if you remember, okay, so what these techniques do, they try to describe the variance in the data. And there are two sources of variance, okay? As we discussed, one is noise and the other one is structure. Okay, and usually you want to get rid of noise and just isolate structure. Okay, PCA does not know which one is which. Okay, it doesn't have that knowledge. But if you look at the distribution of eigenvalues, very often, and if they are ranked, okay, so those are the eigenvalues. And this is the amplitude. Okay, so the first eigenvalue will have the highest amplitude. The second one will have less and less. And what you sometimes observe is that you will have some trend here, but at some point there will be a break. Suddenly it will go to very, very small values. Okay? And often this is the sign of the transition between structure and noise. Okay, so all these eigenvectors encode some variance, and there are two sources for variance, structure or noise. Usually you get structure first, but as you go to higher and higher orders, you transition to the noise. Okay, so the last eigenvectors will typically encode noise fluctuations in the data. Okay, and therefore they will have very low eigenvalues. And you can often see in data sets a break in the distribution of eigenvalues. And that break often is the sign of the transition between structure and noise. And so what you can do, you can decide to use a cut here, and you can project all your data set only on these eigenvectors because you know that this is encoding structure, and you can discard those. Okay, so you do not want to encode the noise. Okay, so you can use that to denoise the data. And you can denoise data using this because the knowledge that goes into these vectors, these eigenvectors, is coming from the entire data set. Okay, so once you have learned from the entire data set, you can go back to individual objects. You can project an object onto this basis set, okay, only encoding structure, and you will have a representation that will denoise your object. Okay, because this representation is not coming from one object, it's coming from the ensemble. Okay, so it has much more knowledge. Okay, so this is another way to say that you should not do data analysis object by object. You should try to learn from the entire sample that you have. You extract the properties, and then you can go back to individual objects, and you have the ability to tell what is signal, what is noise. Yes?
So it seems that what you're saying is, like, for example, if I have a blurry picture, and if I got the noise part from PCA and try to reconstruct the text, will I get a sharper resolution? That sounds a little bit.
So this is going to apply if you have Poisson noise, if you have photon noise, for example. The blurriness is a different effect. It's a spatial effect. Okay? So that's different. PCA, actually, that's on the other side for PCA, as we will see in a minute. But if you add salt and pepper noise, or Poisson noise, or photon noise, it's going to be all encoded by the last eigenvectors. And you can denoise for that, okay? Because the ensemble of your data will know, okay, that those fluctuations are not expected on average. Yes? So it's linear, it's a pro, okay. So what do you mean by linear? Okay. That's right, okay. Let's just stick to PCA for now. So it's linear. Where do you want to put this? Both sides. Okay, let's do that. Okay. All right, so it's linear and it's linear. Okay. Good. All right, what else do we have? Yes?
Similar ways also for these symmetric senses, especially something called difference. The difference is not necessarily asymmetrical, so it simplifies it, which is positive and negative.
Okay.
Variance is only square.
Of course, yeah. Okay, so the first thing I'm going to list here is that, it is based on the mean. Okay, it refers to the mean. Based on the sample mean. Okay, so everything you are going to describe with PCA will be a departure from the mean. And as I said before, if you have two sets of objects, okay, A and B, the mean is going to be halfway in between, and the mean does not correspond to anything you have in your data. Okay, but if you use PCA, you will always, describe a departure from the mean, and that might not be good. Okay. Yes, so PCA is sensitive to outliers. I'm going to write it here. There is also robust PCA, which will take care of that. Okay, so PCA is it's based on the covariance of the data, and if one point is extreme with respect to the rest of the data, it's going to increase the variance enormously. And PCA doesn't know that this is a spatial point. You might know, and so that can drive the eigenvectors to a different direction. If you do it numerically, there are some libraries with robust PCA, so it will first check if you have outliers. In the same way you do a robust mean or a robust sigma, you can do robust PCA, and it can take care of this to some extent. Anything else? Yes? That's right, yeah. So then it's going to be case dependent. Sometimes, if the data just has fluctuations around some mean, and those fluctuations, are physical, PCA will give you eigenvectors that can very well be interpretable. But it's not always the case, and with images, as we've seen, very quickly we depart from that regime. Okay, but often, PCA can give you interpretable eigenvectors, but it's very easy to depart from this. So I'm going to write it as a con. So interpretability is limited. All right, another one.
So all of this assumes that the data that you have is somewhat localized in the space of vectors that you have. If it is disconnected, I don't know if PCA would work this time.
Okay, That's a good point. So what does PCA do? Okay, so PCA is going to go to this high-dimensional space. PCA is only based on the covariance of the data. So it's only a second-order measure of the data. Okay, it's only using second-order moments. And what are second-order moments? We saw that for our astronomical pictures with the blobs. Okay, so PCA is only going to like put a blob on your distribution of points. Okay, an ellipsoidal in dimensions. So if you have some data points, I'll go back to my space of many dimensions, but I will only draw 2 of them. Okay, so if you have something like this, okay, what PCA will do is to approximate this by an ellipse, okay, and your eigenvectors, the first ones, will be like this. Okay, so this is dimension 1, dimension 2, etc. Okay, so in this case, this is a good representation because I have a blob. Okay, but now, what if, as you said, I have 2 blobs? Okay, so some of my images are here and others are there. Okay, PCA can only do one thing, is to basically put ellipses onto that. Okay, so the principal axis here is going to be something like this. Okay, with respect to a mean that does not even exist in the data. Okay. This is not a positive, yes. No, it's on the right side. Okay, so that's one first step, yes?
Similarly, supposing you have a banana.
Exactly, yes. All right, so that's another limitation. So now if the points that I have are distributed like this, okay, the only thing PCA can do is to fit an ellipse to this. Okay, it's an ellipse in n dimensions, but in these 2 dimensions that I'm drawing, it's probably going to be something like this, and I'm not even sure exactly, but you see the point. Okay. So when we have manifolds like this, so the manifold here is this region in which the data points are distributed. If it's not described by just second-order moments or ellipses, then PCA is not going to give us a very good representation. What we would like for something like this is a manifold that will basically follow the data like that. Okay. And what we see here is that the data is actually very one-dimensional. Okay, what you have here is a sequence. Okay, and you could just have one affine parameter which will give you the distance from some origin, and that's all you need to describe the data. Okay, so this is the limitation of PCA. It's actually a serious one as you go to complex data sets, yeah.
Just a question on that, but does that assume that there is like a fundamental representation, like fundamental higher dimensional manifold for your data?
No, you have to find it yourself. PCA will only give you ellipses that will approximate the data. That's it. If it's not, you will have to come up. So if it's not, then it means that PCA is not the best representation for your data, and you have to use other techniques. Okay. And so one issue here, another way to state this limitation, is that PCA is too global. Okay, so imagine, okay, let's go back to the 2 cases. If we have a bimodal distribution, okay, we've seen that if I have one blob, okay, one blob here and one blob there with all my points inside, okay, PCA will try to fit a global ellipse to that, and that's perhaps not good. However, if I now divide my sample into 2 subsamples, okay, so if I first consider this one, okay, PCA will do a good job here. Okay, I will have one representation, and then I do the second one independently, and PCA will do a good job there. Okay, we don't want to do the PCA analysis globally, because then we have to refer to the mean all the time. And similarly, now if I take the limit to many Gaussians, if I have the banana shape, okay. All right, so if I do PCA globally, I will have this big ellipse, and what we see is that it's a crude representation of what I have, but I could do it locally. Okay, so I could just select these points, and I could have PCA here, PCA there, etc. Okay. So basically, this is telling us that when we have these more complex manifolds, we want an approach that's going to be much more local and not a global calculation. Right? Good. Any other item to add on any of the lists? You pick. Lots of cons, okay. Yes?
In image data, PCA is very happy to use the two-dimensional nature of the image.
Very good. Yes. So that's another limitation of PCA. PCA is going to treat every pixel as a dimension, okay, not as a coordinate along one axis with a metric. Okay. So as I showed before, you can shuffle all the data points. PCA doesn't even notice. Oops. My computer ran out of battery. It's waking up. All right. So no, all right, let's see if I can do this. I do, but wait, I can try to switch to my tablet. I don't know if this works. Yes, okay. All right, so we have the pros and cons of PCA. And if you remember, yes. Okay. So this is the same data. We have done some reshuffling. When we do this shuffling of the pixels, we kill all the derivatives. Okay, so we are losing the smoothness property of the data. Okay, and PCA treats all the pixels as different dimensions. Okay, different columns of a table, and you can reorder them the way you want. Okay, and so that can be a good thing or a bad thing. Okay, so PCA is capable of doing, for example, digit recognition on the image that is on the right. It's very difficult for you, but PCA can do that as well on the right or on the left, because it doesn't care about the smoothness of the data. Okay, but as we just heard, now if we have some shifts, okay, so if the digit is shifted, we think of it as a shift in 2D. But in n dimensions, it's actually a change of dimensions, okay? The dimensions are completely reshuffled. And so that can be a bad thing, okay? Because then a small shift of this digit 7 is going to lead to completely different representation in the world of PCA. Okay, so if we want to use PCA efficiently, and actually that's my question coming up for you. Okay, let's think of the following situation. You have some spectra of galaxies that are at different redshifts. Remember that each spectrum can be considered to be a point in a space of, let's say, 2,000 dimensions, the number of wavelengths we have for each spectrum. And the question is, can I apply PCA to this spectra to get a good representation? What would you do to get a good representation? Okay, so here, the key point is that if we have galaxies from a range of redshifts, okay, this is the same as the shift we discussed for the digit. Okay, and so let's imagine we have the same spectrum, but it's been redshifted, to many different redshifts. If you do a PCA analysis on that, you will not get any meaningful eigenvectors. You will get a blur, okay, because it's comparing pixel 10 to pixel 10 to pixel 10 of all the objects that you have. And if pixel 10 corresponds to different redshifts or different res frame wavelengths, the global average of all of that will not give you anything informative. Okay, so if you want to use PCA with spectra, what you need to do first is to go to the res frame of the objects. Okay, then you will have a collection of galaxy spectra in res frame, and then all the features will line up. All the emission lines, the breaks, etc. will line up, and then you can do PCA meaningfully. Okay. So PCA is insensitive to shuffling, but as a result of this, it cannot handle lateral shifts.
Is that true for any distortion? The rotation?
Oh yes, it's true for as soon as you
Size, all those things are out there.
exactly. That's why PCA is not used for image classification, because it is not stable to all these transformations that you mentioned.
But many augmentation things you mentioned before, that standard they use for images, can't be applied to destroy information.
Yes. And so tomorrow's lecture is going to basically be about this. What do we need to do in order to have ways to extract features that are insensitive to many of these transformations? Okay, so PCA is, is useful in many cases, but as soon as you have shifts, rotations, deformations, etc., it's no longer that powerful. Okay. This is an example. Now we have the MNIST data set. We run a PCA analysis on the digits, on the images. And this is the projections in 2 dimensions. So we just keep the first 2 eigenvectors. The different colors encode different digits, 0, 1, 2, etc. And as you can see, it's a bit of a blur. Okay, it's very difficult to distinguish clearly. Of course, there are some trends. Okay, some numbers live more on the left than on the right. But some numbers, if you look at the green points, they are all over the place. Okay. It could be due to many things, and the first thing to say is that the MNIST dataset is already, more or less centered. Okay, the digits are in the middle of the images. There are small shifts of, a pixel or 2, but then there is a lot of deformations. People have different ways of writing a digit, and so as a result, it spreads all the points in that space. All right. So the sensitivity to shuffling can be a good thing or a bad thing. Okay. If the objects we are looking at are affected by this kind of shifts and deformation, it's going to be a bad thing. But keep in mind that PCA is as comfortable, extracting information from this as this. You cannot do that. I cannot. I need this space, but PCA doesn't need that space. All right, so how can we push this to the next level? David already introduced the KL divergence, so I'm going to be brief on this. We can consider those images, those spectra, as distributions. We can assign probabilities to them, and the challenge then is to compute distances, to estimate distances between distributions or between objects. Okay? If I just want to compute the distance between 2 points, okay, this is easy. Okay, there's only one answer. But now if I have distributions, vectors in n dimensions, computing the distances between 2 of them, P and Q, in this slide is not as straightforward, and there are different answers to the question. So something we are going to use is the KL divergence. You heard about it in the previous lecture. You have to keep in mind that this is not a true distance metric. Okay, it's not symmetric. Is this insensitive to shuffling? Okay, so if I remap all the pixels, okay, the I values to a new space, and do I get the same KL divergence? Yes, okay. You apply the same mapping to P and Q, this is unchanged. Okay, so this is going to treat again the pixels as different dimensions, okay, not as a coordinate along one axis. All right, and therefore this is going to be generic. Of course, there will be limitations as we discussed, but that property here makes this very generic. So one way to interpret the KL divergence is that if I have a probability distribution P, okay, and a model Q, and I'm getting more and more data that will give me some p-values, what is the rate at which getting more data will inform me that my model matches the data, the rate at which I'm going to gain this information is described by the KL divergence. Okay, this is what it does, is how much information am I gaining, knowing that, given the model that I have. All right, so we are going to do that now to compare distributions like, for example, the digits or any image, any spectrum, in interesting ways. And so we are going to basically address some of the limitations of PCA using this technique. So this is called the T-distributed stochastic neighbor embedding. Okay, who has used this before? Some of you. Okay. Do you know what it is? Why it is called T-distributed? Okay, we are going to use the T distribution in it, indeed. So what we want to do with this is to go from data points that live in D dimensions, okay, and D can be very large. It can be an image, for example, and we want to project this into something that is that has much lower dimension. Usually it's 2 or 3 dimensions, and this is mostly because we want to do some visualization on the screen. All right, so how to do that? The way this technique operates is to take all the pairs of points that you have in the data set, and we are going to compute a distance between them. That can be a simple Euclidean distance. Okay, you can change and use a different distance if you like, but that's the default that usually comes with the t-SNE technique. Then for every point, given the distances that we've computed, we are going to assign a probability for different points to be the neighbor of the point that we have chosen. Okay, so we turn these distances into probabilities to be a neighbor. All right, and we are doing this in this high dimensional space. Then we want a mapping of this high dimensional space onto something that lives in 2 dimensions. So we are going to introduce a distribution Q, that's our model, that is only in 2 dimensions, and that will also assign probabilities to neighboring points. Once we have this, we can go back up and express that probability in terms of distances, and then we can show that in 2D as an image. Right? Now, t-SNE has to do a mapping between one distribution P to a distribution Q. If we want to do that in a very generic way, one possibility is to use the KL divergence. So what we want to do here is to maximize the similarity between the distribution P and the distribution Q. And once we have done that, we basically have a path that takes us from n dimensions all the way to 2 dimensions. Okay. So again, the idea, I have some data, I compute distances. I'm going to translate these distances into probabilities to be a neighbor of a given point, okay, for all the pairs of points. I have that in n dimensions or d dimensions. I have that in 2 dimensions. So I have a model, and I have my data. I have probability distributions, and I want to maximize the similarity between the 2 of them, and I'm going to use the KL divergence for that. The way this is being implemented is to use a Gaussian distribution here for the probability of being a neighbor. So we expect, if I sit on the data point, the assumption here is that I expect the neighbors to be distributed like a Gaussian distribution. But one twist in this technique is that on the other side, we are not going to use a Gaussian distribution because it's going to be a bit too local. We are going to use a T distribution because it has heavier wings, and it will be more sensitive to points that are farther away than the vicinity of the point you've chosen. Okay, and this is why it's called the t-SNE with a T. All right, so let's see what we can do with this. Now, if we apply this to the MNIST data set, this is what we get. Okay, so now we have a much clearer separation of the different categories of objects, the different digits. And we can do this because we are no longer using one global ellipse to fit the entire data set. We now have a much more local view of the data. And so basically, t-SNE is able to follow the manifold in these kind of configurations, okay, because it's much more local. Okay, for every point, we are going to do the mapping into 2 dimensions by trying to understand which points are neighbors. Okay, so we are ignoring the rest of the data set in a sense. Okay, we are de-emphasizing the rest of the data set. And so by being much more local, t-SNE can express manifolds in a very interesting way. Yes?
The fraction
There is a scale. Yes, there is a variance for the Gaussian and the T distribution, and this is adapted locally, depending on the density of points that you have around you. Yes, and that's a hyper or a free parameter when you run t-SNE. That's called the perplexity parameter. Okay, so if you zoom in some regions of this space, you can see that even within a category, you might find meaningful trends. This is how a 3 starts to blend into a 5 or an 8. And now if you compare PCA and t-SNE for exactly the same data set, there's another technique which is not used anymore these days, isomap. You can see that we had a blur with PCA because of all the properties we discussed, but we have this much better separation using t-SNE. Now this is an example of astronomy data. So what was done here is to take a large set of stellar spectra. Okay, so you have one-dimensional objects now, these spectra. You run t-SNE on them. You project all of these spectra into 2 dimensions to create a map. Okay, so now we have very nice visualization. So we have 2 axes here. Those axes do not mean anything. Those are the 2 dimensions of the t-SNE projection. But what is interesting is that we can start to find interesting regions with different properties. Okay, and so starting from a mess of thousands of spectra, one can reduce the dimensionality and one can obtain very meaningful visualization here. Okay, and you can do that for any data set that you have. So now, in this case, we see that the author of this analysis used only spectra with signal to noise greater than 10. Why do you think they did this? Because they have many more spectra at lower signal to noise. Yes. Mm-hmm. Yes. So what happens if we have noise? Okay. So remember, all these techniques, they can only do something is to deal with variance. Okay, that's the information. And in variance, there is noise and there is structure. And so if we add noise, if we have a manifold like this, and if we have noise in the data, what the noise is going to do is to basically dilate this manifold. Okay. And it's going to look more and more like just a gigantic blob, for which PCA will do a great job, but then we lose all the fine information. Okay, so when you run these kind of techniques, remember that they cannot differentiate between noise and structure. And therefore, if you want to find the interesting manifolds, you should give it objects that are at high signal to noise. Okay, yes? Yes. You don't even need to flatten them because it will work with distances in 2 dimensions. So you just give it a list of objects, a list of 1D vectors or 2D, and it can project them. It will turn each object into a point in this space. But because it's using Euclidean distances to compare the proximity of objects, it can compute the distance in 2D. Yes?
Are there variants of t-SNE which can take into account not just the scalar value, but kind of the uncertainty you have on a particular point when calculating what is likely to be a neighbor?
You can certainly, I don't know of one ready-to-be-used library to do that. It might exist. But given the formalism, you can certainly add that into it because it's all about the probability to be a neighbor. And so you can add a new term which will decrease the probability if you know that the variation is due to noise, for example. So you need to modify it a little bit, but I guess it's feasible. Like, you can imagine of ways to do that. Yes? Yes. Oops. So what was found is that by doing this, okay, so we want to be local, okay, as opposed to PCA, which is fully global. And so it's here we are in many dimensions, and so we can be local using a Gaussian. But now when we project things into 2 dimensions, if we are too local, we are not going to take into account enough information from the rest of the manifold. So here we would like to know a little bit more of what's going on beyond the immediate vicinity. Okay, so by using a T distribution, we have heavier tails. And so we are going to use information from neighbors that are more distant. Okay, and in this case, it's actually a good thing to be able to recover the manifolds when you are in 2 or 3 dimensions. Okay, so if you use a Gaussian, you basically, you are too local. And that's going to, for example, it could break up the manifold into different clusters as opposed to something more continuous. So as I understand, there is no, that's right, there is no mathematical justification for the T distribution. It's an arbitrary choice of a distribution that has a heavier tail. It could be something else. That's right, yes. And in addition, we need to keep in mind that there is a parameter in this. It's the width of these distributions. Okay. All right. Okay. All right, so now let's consider the following images. Okay, so my question to you, are they similar or not? Yes, they are similar. That's what I'm hearing, right? Why? Imagine these were digits, okay? You agree that this would be very different digits. If I run PCA on this, am I going to get anything interesting? No. Why? Yes, pixels are shifted around, and there's even much more than that going on. Okay, but you are telling me that these images are similar. Why? What makes them similar? There are some correlations there, that's right. Now let's consider these ones. Are they all similar, or are there 2 categories here? 2 categories? Okay. What makes them similar within 1 category and dissimilar between 2 categories? Yes, but without using the word brick, can you be more? I mean, there are also, yes, you can find, I mean, there are lots of one-dimensional features there. The texture is different between the 2 categories, but the same within 1 category. So, but now, why? What makes the texture different or similar? Parallel lines. Okay, I can come up with all sorts of parallel lines that will, let's see. Okay, this is a good example, okay? Wood. Okay, what makes this wood? What makes this wood? Okay, what makes this one wood? You might say the texture is the same, but I would like, you to tell a computer how to recognize that this is wood. Is that going to be sufficient to describe all the wooden patterns and exclude everything else? Okay, so we have basically one word for this in English, but there is a huge variety of possible wooden patterns, right? They can be straight lines, they can be short lines, long lines, they can be, you know, more complicated lines that intersect. They can be circular patterns in the wood, etc. Okay, so this space is actually very, very rich, even though in English we have one or just, you know, a limited number of words to express it. Okay. And so this is the world of textures, indeed. And very often, as we start talking about textures, this is where we find the end of what our language allows us to express. Okay, if you think about it, textures, usually they are the things that we don't want to define with too much detail. Okay. It's, in some sense, sometimes some boundary between what we can describe and what we cannot describe. Describing this is extremely difficult. And this is basically the challenge that is at, you know, the core of image classification. You know, how can you do this simply? But then how can you teach a computer to do that? Okay. Again, here PCA will not help you at all. And you were right previously. Whoops. Okay, so those are different realizations of an n-body simulation that has the same, you know, cosmological parameters and everything. So in some sense, they are the same. But now if I compare, you know, pixels one-to-one or regions to regions, they are completely different. But there are similarities that we can extract by eye that makes us say that they are similar, but trying to express them is very difficult. Okay, now if we want to do that in the computer, we have to tell the computer how to do it. And so here there are two ways. I mean, there is what you know already, how to use neural nets to do this. And the idea is not to try to describe what you see, but to just use lots of examples and have the computer extract interesting features from them in some mysterious way, because it all happens inside the black box. Or there is a different approach, which some mathematicians have followed for the past 10 years, is actually to try to write down, you know, equations, if you want, to try to express what makes these images similar. And so that's going to be the topic of my next lecture, okay, how to define the similarity in these images. And this is going to be really one of the core ideas that allow neural nets to do classification with these very complex images. And the question is, how complex are they? If you can do this just like that without thinking, perhaps the apparent complexity is not as high as it looks. But the challenge here is to find the right language that will allow us to turn these objects into simpler representations that will be useful to disentangle different categories. So I'm going to probably stop here for today. And what we are going to see tomorrow is what kind of mathematics we can use to have an efficient representation of these different textures to teach a computer how to recognize one from the other. Thank you.